go. Yeah, Chlorophyllum mollibites are poisonous to most humans. Okay, good. Yeah, it makes sense. Oh, good. I'm glad you reminded me of that, Emily. People, oysters. What we got on oysters? Anyway, yeah, you always like, how did someone ever think, oh, that'd be a good thing to eat? Looking at the outside of an oyster. Well, oftentimes, early humans, what we did is we watched other animals, like otters will eat oysters, right? They roll in their back and take a rock and they beat on it. Apparently, there's a special type of rock, or they have preferences for the types of rocks. It's very weird. Hi, Penny. Good morning. There was this young otter at SeaWorld. I remember one time I was playing with a rock, so I was just figured, oh, like a ball, go fetch. I don't know. It's an otter, right? So I went to grab that rock, and it bit the snot out of me. Like, my rock. I'm like, fine. Not so cute anymore. But so they open that up and they eat that thing out of it. That's oftentimes what early humans may have done. They may have watched other animals eat this thing related to us, mammals, or if they had some understanding. I don't know if everybody didn't have understand of relatedness. But like they saw a horse eat something, a wild horse, they might think, oh, maybe we can eat that, And then maybe after that, they just sat around and drew straws. I am on video. Anybody else seeing me? My German teacher, Arbeiten zusammen. Working together. Let's remember her doing that. Go off in groups and Arbeiten zusammen, really. It's the only German I remember. I don't know, Jordan. So if we look at the at a picture of planet Earth from a distance there, right? We see this. We see that it's a lot of blue, my favorite color. It's just so it coincides. But if we do that, what is the blue on Earth? Not a trick question. What is the blue? What is the Earth mostly made up of? Why are we called a blue planet? What is that stuff? Yeah, absolutely. So water, we take it for granted every day. It's no big deal, right? We take it for granted how much we have. We take it for granted that it's always going to be there. But even if you look at water in terms of what it is, I remember asking my dad as a kid, Dad, what's water? And he'd say, well, it's 2 parts of hydrogen and 1 part of oxygen. Yeah, we could have a slow connection, Jordan. Let me see. Jordan. Yeah, it says that your connection is okay, whatever that means. It'll fade in and out. If it's a real problem, and we see with other folks, I can turn the video off. I'll do that. So he'd tell me, 2 hydrogen atoms. He didn't say atoms and 1 part oxygen. He said it was always funny to him that even as a little kid, I was like, okay, like how the heck? What's hydrogen and oxygen? I guess maybe I thought of it was like flour and sugar, and you made water. Just seems to my dad, it was just so easy for me to accept that explanation. Didn't even care what that stuff was, but. Anyway, so this is what water does, or this is what water is, this is what water does, right? Water has that really, really unique property of sticking together. Now, it's not a very strong attraction, not a very strong sticking together, easily broken, right? Take a pitcher of water, glass of water, tip that pitcher up, it's not like, oh, I'm struggling against the water flowing over the edge because it's holding on so tightly to the next one that's going over the edge, pulling it with you like paper clips, right, or something that you would stick together. Oh, good. Excellent. But nonetheless, that bond is important, right? It's important for us. As a matter of fact, it's so important. I heard this thing one time in chemistry that said that if you look at elements similar to water, similar in terms of other chemical properties, weight maybe. I think benzene is what they use. Is it? Maybe not. Anyway, if you look at other chemical compounds that are like water in ways other than the hydrogen bonds, that on Earth, with the temperatures that Earth normally experiences being, where it is from the sun, these things should exist mostly as a gas. So I'd be showing you a picture of rock and a gaseous planet, like a Jupiter-ish kind of thing. And life as we know it doesn't do so well in gaseous water. It can't live in gaseous water. We can't live in solid water. No, there are things that can live in ice, but they're not living in solid water. Their bodies are not solid water. Of course, liquid water is the thing that we normally think about. And those slight attractive bonds are everything about who we are. Nah, not much, Jordan. We were just basically talking about water and its unique properties, right? The fact that it has this ability to just slightly hold itself together because of those polar covalent bonds. I don't want to go all the way back through that. Make sure you review as to why I'm calling those polar covalent bonds and why there's a connection there, why they make the hydrogen bonds, right? So they stick together just a little bit. So the next slide I'm going to come back to a few times throughout lectures. So don't worry when I go on to the next one, because I want to talk about these properties of water in order, and I'm just going to kind of keep this as reference. Okay, so the first part about water, the first property of water, kind of fits with what I just been talking about, right? It has this property of cohesion. Why don't you add another word to that? Call it adhesion. So just AD instead of CO. Two things. They're two different things. I'll explain them to you, but put that on there just so you kind of remember. And now it doesn't really fit with the explanation because cohesion and adhesion do have a different explanation, a different definition. I'll get that in just a minute. But anyway, things stick together, right? And if you look at the chemical reason behind this, and this is where I love where we are in the terms of the class, right? We're at that point where I'm starting to kind of jump from the chemical things that atoms, which aren't alive, do, molecules do, water molecules, things that they do, the ways that they act, that are just chemical things, like rocks falling off of a boulder, off of a cliff, react to gravity. Gravity's not a living thing pulling it down. Water sticks to each other through hydrogen bonds, not because it's like, oh, come here, hydrogen bond, you and I are going to hang out and hook arms and whatever, right? It doesn't work that way. This is all like magnets. They don't think when they stick together, for example. It's I always tell folks that living organisms are just this really cool, kind of complicated chemical dance that's going on. Man, that's just blows me away, right? So anyway, water molecules sticking together. Yes, physics, chemistry, blah, blah, blah. We're doing it before we came along. What does that allow for us, all right? So I get you some explanations or examples how it helps us, but let me show you. I get better, right? Look at this, the tree. See the tree? How does water get up a tree, man? Gravity. You know, if you're like my wife, I'm like, Millie, don't water the leaves. They don't take water in through their leaves. No, they like it. And that's back to that I tell you about her talking to plants, right? So anyway, yeah, it doesn't come up from the leaves. So anyway, think about it intuitively. So water goes against the force of gravity, does it not? We know water falls down. That's what happens in rain, doesn't it? So water goes. So if you think about this property that water has, now whether you're talking about something alive like a tree or go over there to your graduated cylinder. Look at that. Didn't it do this in lab the other day with our didn't it curl? Not as much in those plastic ones, but if you looked at the glass ones at the back, which I hope you did, you'll notice, especially when they got really small, these graduated cylinders, there was a lot of that. Y'all remember what that's called? That curly thing. That curl of the water. It's not really a curl, right? It's like an indent in the water. So water's actually being, yeah. Spelling's close enough. But it's called a meniscus. I think it's CUS. There we go. So it's because of the fact that water molecules can engage in this this thing of cohesion where they stick together, but they can also stick to the glass. That's where the difference in the definition comes. Okay. That's okay. Right? Adhesion is with something sticks together that's different, and cohesion is when something sticks to something like itself. Water sticks together. Water molecules stick together through cohesion. They stick to glass. Okay? They stick to the side of a tree. If you cut open a tree and used an electron microscope, which are really cool. He's the one at the University of Georgia in Athens one time with this guy who was doing some work. I was helping him. He was doing I don't remember exactly what he was doing, but the pictures that we could get were incredible. So they take this section through a tree, and what I'm trying to show you is if you look, cross-section through a tree, it's pipes. It's a bunch of pipes. You probably already know this. That's how the water gets up there. And specifically, the water sticks to the sides of these conducting cells, these pipes, through adhesion, and then, of course, which helps keep it up stuck on the wall, and then cohesion sticks the water molecules together. Now, how the water travels up the tree is because, and we'll talk about this in I don't know what chapter that is, photosynthesis. for reasons that living things can't dry out. It helps the tree from dehydrating, obviously, but photosynthesis uses these molecules. Come on, pen, really? There we go. It uses them. So something up there in the leaves is taking these water molecules. So it's like everything's being pulled along. All right. The adhesive forces also are beneficial in the sense that the attraction, this is a physics thing, the adhesion forces are generally greater. I put this little black text there, than cohesion. So in the a graduated cylinder, the glass sticks more heavily, whatever, to the water than the water sticks to itself. These are really slight forces, aren't they? But yet, it's cool that it's really neat when you look at it and you go realize what's happening. You're watching or seeing molecules interact with each other. Right? The other day, you probably just like, what? Oh yeah, for fun. What's the volume there? Read that graduate cylinder to me. How many mLs of liquid do I have? Put this down so I don't forget. Come on, should take it. If it's lab practical, you don't have this time. There you go. Yeah, 20.6. Right there you go. Bottom of the meniscus. There's 20. That line right there, and then each one of the ones is 2, 4, 6, 8. Each one is 0.2. All right. If you're having problems with that, see me in lab. Oh yeah, cool. Check this out. There's other examples of water sticking together. Cohesion now, right? So you can even do this. I don't know, some of you might have. I did it in a lab one time, remember, when I was a kid in high school. We floated a dime, though. But you can float a needle, that's a sewing needle, or a dime on the surface of water, right? Insects do this. You see this, the water strider at the bottom. Some spiders up there. Look at that spider. Isn't that cool? He looks like he's walking on like a comforter, right? And you see it in the needle, you can see with the way the picture is, there's a reflection. There's an indentation there. And the water strider, not as much as as our arachnid buddy up there. Yeah, Courtney, are you arachnophobe? Oh, come on. No, they're fine. They're fine. All of them have poisonous fangs, but most of them don't bother you. Anyway, they're just creepy. My daughter-in-law grew up in Australia, and she did I tell you guys about huntsman spiders? Yeah, I won't show you that again, but anyway, yeah. So the water strider, check it out. A little bit of indentation. Now, what I just told you about water molecules and this property of hydrogen bonds that we've been discussing, explain to me what you're seeing here, like with the spider, or the needle, or the water strider. Why does it look like the spider's walking on a comforter? Why do we have these indentations in the water? If you're thinking, oh, there's a name for that, 2 words, it's surface tension. I'll give you that, but what does that mean? Great, I'm glad you said pushing, right? Right, we're pushing on the bonds. Which bonds? Which bonds is Brandon talking about? Right, you guys are saying, that's good, that's good. Which bonds? Between the water molecules, right? So what that little spider, that needle, and that water strider are gently doing there, maybe it's a big spider, I'm not sure. Well, no, it can't be too big. Is it's just barely pushing down, because those bonds exist. Yeah. I mean, if you just barely upset that needle, it'd go to the bottom. You could break the surface tension very easily. These insects have evolved, isn't that neat? They've evolved to learn how to just kind of stay. And there's a lizard that can do it, the Jesus lizard, they call it, because it can actually, if it has to get a running start on land, but as it walks across the water, its feet barely hit the surface of the water, so it actually and this is look it up online, and this is a full-grown animal that's doing this, right? So it's like the guy walking over or person walking over hot coals. You're gonna do it quick, right? So those hydrogen bonds, really neat, huh? I mean, that's kind of cool. They're so slight, we don't ever think about it. Every day we go, yeah, hydrogen bonds, whatever, or water, who cares? But it has these really magical kind of properties, really neat type of properties that organisms show us, Next time you see some critter crawling on the water like that, take a look at it and see if you can see the indentations. What does? Which one? None of them look like dinosaurs. Yeah, it does. Sorry. Yeah, the Jesus lizard does. It's cool. The name comes from its ability to walk on water, in case you were just thinking, where did it get its name? What's the next one? Oh, the next one. We know this very well in Florida, right? If you're outside, especially in the hot summer sun, and you're not hydrating, and for reasons that I'm going to help you understand here in a second, we do not cool very well here in Florida, us humans. It's very difficult to keep ourselves cool. Do you know what I mean by that? Why is it so difficult to stay cool in Florida? Yes, I know it's hot, but we do sweat a lot, right? But we don't. It's something we got to keep our eye on here in Florida. It's real easy to overheat. Yeah, it does. Yeah, humidity, right? So the humidity, basically, if you think about it, is the water in the air. So since we have such high humidity, the water on our body doesn't want to go to the water in the air. Remember, things in chemistry are kind of like things in physics. They go higher to lower. So where there's more water, it wants to go where there's less water. Well, if it's dripping wet outside, which you know what I'm talking about, right? Your skin, all that sweat on there stays there. And when that sweat stays on your skin, it doesn't evaporate. Now, the next two properties are what I'm leading on to. I put them together, and we're going to talk about them individually, what exactly they mean, but they kind of mean the same thing, chemistry-wise or physics-wise, and they really mean the same thing biological-wise. So I've united them down together to tell you that the second two properties of water for organisms, living things, the benefits to life, it means that we can allow us to moderate our temperature, to keep it back, keep it homeostasis. Wish I knew the German word for that. I don't. Should have asked my German student. Homeostasis, things in balance. You get hot, you sweat. Why does sweating work? Well, sweating works because of a physical property, okay? It's the high heat of vaporization. It's the third one down, the second of those two I'm talking about, right? Look what it says over on the right-hand side, the benefits to life. When water cools off of a surface, cement, rock, anything that's not living, it removes heat. Laws of physics. A hot rock sitting outside, if I threw water on it, would cool, would it not? Yes, it would. Same thing with you. Same thing with you. You just take advantage of that physical property. See what I mean? That life is this dance of chemistry and physics where living things have just learned how to kind of manipulate and use the things that are going to happen in Mother Nature anyway, right? This lot, that becomes yeah, that's not a lie, but it cools off, right? Because it's losing heat to the air. The air is not as warm, okay? So how does that work in terms of the chemistry behind that? So how does that work? How does this evaporation of water cools our body surface? How does that tie back to the chemistry? I mean, what does it mean here when it says a lot of hydrogen bonds have to be broken for water to evaporate? So let me, I got some terminology that I got to go over with you, and I'm trying to find a good place to think about introducing that, but I don't think I'm going to do it right now. I think this is what I'm talking about. I'll get back to that in a second. I want to stick with this thought that's in my head that I'm trying to explain to y'all. Water molecules have hydrogen bonds. Hydrogen bonds are springy. So you notice in this picture, that's exactly what I've done. I've replaced them with springs, okay? So what we mean by that is to break the bonds between water molecules, it's not a said and done deal. They vibrate. And the reason they vibrate is because they absorb energy. And the energy they're absorbing, specifically that I'm trying to get to, is heat. So when you warm up, and now this is where those two properties that I'm talking about kind of start blending into one another. When you warm up, the water molecules in your body, on your body, they begin vibrating back and forth on these springs. The more you warm up, or the more it warms up, the faster they vibrate. Faster. Now, what does that mean to you? The energy that's making those springs go back and forth is otherwise energy that would overheat your body. It's the same thing that's happening in your car. The car has some coolant in it, so it has molecules that do basically the same thing. But what they do is the water in there, I mean, years ago, that's what we used, was just old water. Those springs between the hydrogen bonds, or the springs between the water molecules, which are hydrogen bonds, are bouncing back and forth. And they're absorbing the heat. Your body isn't. We're going to talk later on about enzymes and all kinds of other things, and heat, bad. much heat is bad. It makes things twist and distort out of shape, and that's not good for living things. You see what I mean? So you're absorbing that heat, and then finally, and this is again where I'm starting to put those concepts together. I'm gonna jump back to that slide so you can put the words and the pictures together. Finally, enough heat is added. Finally, enough energy is added. It bust apart. Okay. Now, here's where I'm going to remind you a little bit of your terminology when you were just a kid in school in science. When something that's liquid gets further apart, busts apart, goes away from each other, becomes less and dense, we call it a gas, don't we? Everybody good with me on that? Right, so you boil liquid water, it becomes gaseous water. We call it steam. And then the other way, conversely, the other way, right? When things get very, very close together, we call them what do we call them? Call them a solid, don't we? Yeah, so I'm talking about water freezing, and I'm talking about water evaporating. When water evaporates on your skin, these springs, okay, back and forth, oh, too much heat. Boom, when it evaporates, it removes a lot of heat from your body. So you get the lead up to it with the springs bouncing. They're absorbing the heat, right? Everything's going, we're cool, right? This is like, I think about this when I'm running so much because that's what happens. I'll sweat and I'm not evaporating. I'm not removing any heat. So I'm constantly making sure that I'm sweating because y'all understand that, right? When you're outside, if you're sweating, that's good. When you stop sweating, there's something wrong. You know to go inside, right? Everybody knew that. Didn't everybody shake their head? Can't do that, but everybody knew that, right? If you're outside sweating and all of a sudden you notice you're not sweating, you need to go inside. That's the sign of heat stroke or heat exhaustion, which could be heat stroke. So when those molecules finally do separate and become steam, they remove a lot of heat. So you get the lead up of the remove of heat, then you get the release of heat when things evaporate. But here's a problem for living things. This is the dehydration thing. I was running the other day and went by a nursing care facility place, and a woman passed me going the other way, and I was sweating pretty good, and she said, "Remain hydrated." And I thought to myself, I'll bet you $1 million that's a nurse. I can't think of any other, of course, where I was walking helped, but I can't imagine anybody else would think about that passing in me as I was running by them. I thought, well, that's a nurse. Can't help but be a nurse. But, of course, the reason what she was reminding me about was the fact that when that water evaporates off your surface, that's a good thing. Yes, of course, it cools you. That's the whole point. But it's gone now. And there's less of these molecules in your body that can do the bouncy thing before they evaporate, you see? So you need the water, and losing the water helps you, but the point is you got to replace that water. So, again, let's go back and see how these two things fit together. The high specific heat of water explanation. Hydrogen bonds can absorb heat when they break and release heat when they form, blah, blah, blah. What I mean, that first part means those springs that I was just talking to you about, they can absorb a lot of energy. High specific heat. What we can say is high heat tolerance, maybe is a better way to say it. Just never thought about that, but that's actually not bad. High heat tolerance. Water can absorb a lot of heat, right? So that what's in it, your engine, your body, whatever, doesn't get hot. So that's why water in living organisms stabilizes the temperature. It does what's that thing called? Teeter-totter, seesaw, back and forth. Finally, when the thing gets very warm, the water, when it evaporates, high heat of vaporization, right? I'm trying to think of a way to reword that. Well, I can't. When water evaporates, it removes a lot of heat. So it cools it off. So one leads into the other. Water has high specific heat, and then it also has high heat of vaporization. So it can absorb a lot of heat, and when it finally does have to go gaseous, gotta go gaseous. Density is decreased to the point where I'm not close enough to be considered a liquid. Therefore, the liquids have thrown me out, and I'm a gas. But when that does, lots of heat gets released. Lots. Remember I said you got to put it back, right? Got to put it back. Anybody got any questions? I'm going to do some terminology stuff for you here. Some stuff you got to know because it's stuff that you might see later on. Not maybe so much in this class, but some of these words you do see, actually. We're all good? If I need to check you on roll, and because I did and I forgot because some people came in, make sure you get with me in class like athletes or something like that. You can get to this whole thing later, Penny. I'll post this in the recorded lectures. On the left, it says recorded lectures in the blue part on Blackboard. There's a folder that says class lectures. Jordan, did I get you? Let me see. Yeah, I did, Jordan. I got you. All right, so what I've been saying is the water absorbs heat before it turns into gaseous water, so it can act like a regulator. You see, it can act like the thing in your car that I'm talking about. It can act like the radiator of your car, which what it's doing is the liquid that's in there that's cycling through the engine is absorbing the heat of the engine. We all know what happens, you know, if your coolant system busts down, right? It don't take long because the internal combustion engine generates a lot of heat. Here's a good question for you. Out of a gallon of gas, what percent of that actually moves your car? What percent of that makes your engine hot, which doesn't move your car? So what percent, how much in a gallon of gas, what's efficiency? What's the efficiency? How much actually does what it's supposed to do, move the car? You're going to be surprised unless somebody knows the answer. Nobody? Come on, I can guess. If I'm sitting here talking to you about it, it must be like probably opposite of what you're assuming. Yeah, I get you. A little bit higher than that, a little bit lower than that. Yeah. From what I heard, the average is around 30 to 35%. So that gallon of gas, only about 30 or 35% of it moves the car forward. The other 65 to 70% makes the engine hot. There's nothing you can do about that. That's basically, we say heat, and it's kind of one of those things where you're like, what? But we say it can be considered wasted energy. It's disorganized energy. Doesn't mean we can't do things with it, but it's not a precise form of energy. Okay, so but like I said, one of the things we can do with it is as a regulator. I showed you about it in your body. I'm going to show you here in just a second how it does on the Earth as well. Water can absorb. It can release a lot of heat. It doesn't change its temperature a lot. Now, the reason why that second part is important. Because, oh, come on, pencil, really? When temperature changes occur, things change state. Remember? That's how you melt ice, get it warmer. That's how you freeze water, get it cooler, right? That's what happens. So it's back to that evaporative thing. Water can absorb and release a lot of heat with a slight change in temperature. Thank goodness, because it jumped really quick, it would quickly become gas and it wouldn't help us. So remember, water's bouncing. I'm not going to be a gas yet. Oh, now I'm a gas. Right? If you took a spring and pulled, it would come apart, wouldn't it? I mentioned you what specific heat is, right? The amount of heat that must be absorbed or lost. This is the technical definition, and I put in highlights so you know the standards. It's 1 gram of a substance to change its temperature by 1 degree Celsius. In the case of water, that heat can be designated, can be called calories. That's what calories are. That's the word I said before that you all know. Calories are heat. They're energy. When you go and you buy a candy bar or something, it says, I don't know, 200 calories. How did they figure that out? Does anybody know? How did they figure out that Snickers probably got more than that? But how do they figure out the calories in food? Thank you, Jordan. That's right. Any more specifically? I always spell this wrong, so I'm going to look it up while I'm talking to you guys here. Because it's got a really cool name. Oh, now I'm lost. Where's the screen? Oh, there we go. Yeah, there you go. Yep, there you go. They blow it up. They put it in a bomb calorimeter. Yeah, good job, guys. They put it in a bomb. They blow it up, and the amount of energy it gives off is the amount of calories it is, right? Because things blowing up, giving off energy, it's all the same thing, right? That's what it's doing in your body. As we're going to learn in respiration, you release it in a controlled explosion. And if you're kind of going, what's he mean by that? Think of the difference between the gas going into the engine of your car being squirted in by the fuel injectors now, probably for the most part, just a little bit at a time, and doing its internal combustion thing, making the piston move, all that stuff. Or throwing a lit match into a gallon of gas. One releases the energy, right? But the other one, I don't like Snickers. You know, I have Mounds Bar, I love coconut. But the other one, you throw it into the gallon of the gas, boom, releases it all at the same time. Two ways to release energy, right? So we can define calorie as energy. So that's the amount of heat, which is energy again, to raise 1 gram of water 1 degree Celsius. Don't get confused with what the calorie is versus high specific heat or specific heat in general. Calorie is talking about water, right? The amount of heat required to raise the temperature of 1 gram of water. Specific heat could be talking about liquid vinegar. Well, not liquid vinegar, vinegar. Now, those terms can be a little bit confusing, and I'm not going to make you do any calculations with them. You know, I may want you to know the definition, so you should know that. And remember, they're related to one another. One is just specific for water. But to be honest with you, the take-home message, and if I were going to really expand in anything in terms of a question, if I were going to ask a question on this, would be what it says down below by the arrow. Basically, what this all says, the moderation of temperature by water. Please take a look at my slides when you look at them. I have tried to lay them out so that, you know, especially when there's some text on it like this, so there's some way to follow the logic. This is what I'm talking about. I remember in college sometimes taking notes and then standing back for a second going, what's this guy talking about again, right? Getting lost. My ichthyology professor was awful about that. So that's why I try to, he's a great guy, great professor, but my goodness. So that's why I try moderation of temperature by water. So the bottom line is, water, very important for us, makes up most of our body, makes up most of the world. I'm going to show you in just a second how the world uses it versus just in our bodies, right? But water inside of us, and there's a lot of it, water is this substance that works just like the radiator in your car. It allows our body to be exposed to cool conditions. It allows our body to be exposed to warm conditions. It allows our body to warm up. It allows our body to cool down. It allows our body to do all those things that are necessary, just like our car needs, so it keeps working, right? The thing again, teeter-totter, seesaw. Which one is it called? It's both, right? Is there a difference between a teeter-totter and a seesaw? Or are people going, I remember, what did that guy in college always? Up to my neck in a crick. I'm like, what is a nick or a crick? Okay, this idea of water being absorbing and releasing heat, and it works in your engine, right, exactly. Works in your engine, it works on the planet Earth. So let me show you the little map down below what I'm talking about. I lived in San Diego when I was in the Navy. Wonderful place to live, wonderful place to live. Very crowded, beautiful, but I would say the best thing about San Diego had to be the weather. It was moderate almost all year round. I don't remember, other than at night, and that's for reasons that I'm going to get to here a little bit, San Diego and Southern California can get pretty doggone cold at night. But during the day, February, July, it didn't matter. It was always right about in the 70s. It was beautiful. It's gorgeous, gorgeous weather. But you notice when you look at this map, it doesn't take very long when you get away from the coast, like you get up to Santa Ana. I've been to San Bernardino in the summertime. It gets blazing hot. Look, Palm Springs, 106. I mean, down here in Florida, we get that kind of temperature with the heat index. But I remember growing up in El Paso, oh, God, it'd be common for 2 weeks of 100-plus temperatures. My buddy worked in Saudi Arabia for a while. He said that it would get so hot that the tires only lasted a little bit over there because they would literally melt onto the pavement. It would get so hot. It's amazing. But what does, why is San Diego so nice, and considering the fact it's warm, and, we would think of it being a place kind of like Florida where it might be hot and humid. Well, it's nice because it's not humid. And one of the reasons it's not humid is because it's got this cool, way too cool for me, by the way. I'm a biggest wimp when it comes to temperature, 68-degree Pacific Ocean. To give you an idea, if you're going, the springs in Florida are consistent at 72, I believe. There you go. Thank you, Seth. Perfect. So we're talking 4 degrees cooler. I did not like the ocean out there. I would only go into it to cool off for a little bit. People don't sit there and splash around in the ocean the way they do out here. But that cool ocean sitting right off the coast, when the sun would come up, the water would absorb most of the heat. So some would go on the land, so San Diego would warm up, right? But most of the heat, or most of the energy, the heat, would go into the ocean, right? Just like it would go into the water of your car, your engine, and the radiator, and the same thing they're talking about in a human, right? So I'm just kind of taking the human model and blowing up into a bigger thing. So the further you got away from the ocean, which is why Santa Ana and Burbank and Palm Springs and all them places got hotter and hotter, is because they were further away from that effect of the ocean being able to do that. So San Diego without the Pacific Ocean is going to be as hot as Palm Springs. But sitting out there with that nice, cool Pacific Ocean, it is cold, boy, I tell you. But I went up to Maine in the summer. It was, put my toe in the water. I think it was going to freeze off. Like I said, I'm putting on a wetsuit when I scuba dive when it drops below 80. Or even below 85, to be honest. But like I said, so the Pacific Ocean acts as this nice regulator. Now, at nighttime, when the sun goes down, what the Pacific Ocean does, or what the ocean does, what water does, and it just happened in the Pacific. And we see this in Florida, too. At night, when you would like it to cool off in Florida, last night I'm watching the news and it's still 80. I'm like, oh, my goodness, right? Anyway, so at night, the ocean then releases the heat. So during the day, it absorbs, let's call it excess. It's not really that, but absorbs the excess or a lot of heat. And at night, it begins to release that. So it moderates it. It keeps it from going, look at Mars. That's Mars in the upper left. And like Elton John says, Mars is cold as hell. It's not a place where you'd want to live because it doesn't have water. It might have subterranean water too, by the way. So, but what we know about Mars is at night, the temperature drops to minus 75 Celsius, so minus 103 Fahrenheit, if you're still sticking with that. And during the day, it gets to a nice balmy freezing. Today's weather on Mars, it'll rise to a balmy freezing, so make sure you stay hydrated, folks. Right? So that's your day on Mars. Now, if Mars had water, it wouldn't be as warm as Earth. It couldn't be because it's further away than we are. Another 100 million miles. 100 million miles is Mercury. 200 is Venus. No, it's not that way. Anyway, I forgot, but it's further than us. I had a way to try to remember that, and then I forgot it. But see, without the ocean, Mars is doing that during the day. Well, my God, how do you dress for that? Right? How do you dress for that? I mean, minus 75, you just don't go out. To me, anything below 60, you don't go out. All right? So next time you're out in San Diego enjoying the good weather, make sure you understand why it's good weather. I mean, I remember going to San Diego in February, laying on the beach, it'd be 70. Oh, gosh, I almost forgot about this, but yeah, I love Oceanside, me too. So we're still sticking with those two, right? Let's get into evaporative cooling or heat of vaporization again. Remember, that's what I'm talking about. The heat of vaporization, and I define it again for you there, is how much heat, could be calories. There's another measurement of heat, folks, that you might have heard about if you've taken physics you did, called joules. Not like jewels in your hat or nothing, but anyway. So heat of vaporization, amount of heat, 1 gram of liquid must absorb to be converted into gas, okay? So, in the terms of when we define a calorie, we're talking about that amount of heat for 1 gram of liquid being water. All right, so here's what basically that tells you. When something evaporates off of a surface, right, you get a heat transfer. It's the springy thing. So the dude on the left who's working up a good old sweat in the middle of the summer, what's happening is as the water is coming to the surface of his skin, as it's evaporating, those springs are breaking, and a lot of energy is getting removed. Now, he's got to remember to keep hydrating because he's losing water. So it's like the last-ditch ability for water to absorb heat. It's been springing. It can't spring any further. That spring is sprung, and he popped out. Why do I have a picture of a Thompson's gazelle? Because check this out, man. I love this kind of stuff. Thompson gazelles have a brain. Everybody knows it's not good to get your brain too hot. So how does evaporative cooling help a Thompson gazelle keep its brain cool? Well, if you take a look at the way the blood flows, it's absolutely incredible. And let me remind you, an artery is what's delivering blood from the heart, right, as it's making its way through the body. So the heart goes, the blood goes back to the heart, then it gets pumped out in the carotid artery. So this is going in this direction. That big white thing is the esophagus. That's not an artery or vein or an artery. There's the spinal cord. And then veins bring blood back to the heart. All right, everybody remembers how that works more or less? If you don't, that is how it works. Arteries bring blood away from it. Now, as the carotid artery begins flowing up into the head of the gazelle, which it needs to do, because like every place, you got to have blood flow, it's been warmed. All right, it's been warmed by the body. And the body's warm because the thing lives in the doggone not desert, but lives in the savannas of Africa. So it's hot, right? It's hot there. So in them really, really hot days, even the elephants are flapping the ears. You ever see that? That's what they're doing. They're cooling off. Jesus, it's like you're taking this thing and doing that. So that blood that's coming up the carotid artery is actually so hot. It doesn't have to be hot. It's too warm that if it got near the blood at that, or brain at that temperature, if it got near the brain at that temperature, it would overheat the brain. And the poor animal would, when you start overheating the brain, you'd go into neurologic problems, you'd wig out, and the critter would die, okay? So evolution has come up with this incredibly clever way to take care of that problem. Follow the arrow. As that carotid artery blood, warm blood, makes its way toward the brain. It doesn't go to the brain right away. It goes into this thing where there's this sort of a, call it a roundhouse where the trains used to come together. Think about it as an interchange. There we go. It comes into this interchange where the warm blood is not routed by the brain. It's routed into the nasal passages first. All right, then it comes back out of the, I'll get to that in a minute. It comes back out of the nasal passages, back into the interchange, and then it travels down the jugular vein back into the rest of the body. The purpose of this is to cool the blood before it gets to the brain, and of course into the rest of the body as well. Now, how does cooling the blood get done in the nasal passages? It's evaporative cooling again. As this animal is breathing in air, right? There's liquid in the air, and air itself is going to absorb heat. That's why Dorian told me about the cooling off pot. So as the animal's inhaling, he's inhaling air, moving air, and liquid, depending, how humid it is outside, across this warmed up air that's in all those little Y's that's drawn there, cooling the blood. Then it goes back into that interchange by the brain. Is that incredible? I didn't learn that till a few years ago. I was like, oh, good God, that's incredible. I'm going to talk about that in class. Think about the years of evolution and how this critter adapted to its environment. Yeah, probably. They got to be good smellers, too, because they're prey. Okay. All right, I got a question. Let me go back to that that sheet again. We got any questions of what we've gone over so far? So let's remind ourselves. Yesterday, the lag was awful. It took me forever to do this. Okay, we've gone through water sticking together. We've talked about why it sticks together and how we living things use that. We talked about this temperature moderation thing. We talked about the fact that, yeah, no kidding. Very crowded, but I love California. We talked about the fact that it absorbs a lot of heat while it's springing and then really releases a lot of heat when it evaporates, but that's problematic because you got to rehydrate. The fourth one down, lower density of ice. Let me ask you a question first before we get into that. It's again one of those things where I ask people questions because I want to remind them that in the world, when we try thinking about scientific concepts, we really do have an understanding of them already. Sometimes in science, what we do is we put words or structure on something you already know. I did that with the scientific method, remember? Remember I showed you guys this isn't always used for curing cancer. We sometimes use it to figure out what we're going to wear in that day, right? It's just the way our body works. So let me ask you one of those questions. I take ice, frozen water, right? And I drop it into a glass of water. What does it do? Come on, guys, not a trick question. Emily and Courtney, you have sinks. Does anybody agree with Emily and Courtney that that would sink? The rest of you say float. It does melt too, Penny. Yeah, especially if it's warm water. Hate that when they give me my iced tea with too warm. Emily and Courtney said sink. Does anybody agree with them? No, nobody agrees. They're wrong, right? They're wrong because when we look at it, we obviously know that's not what's happening. But you know, they're also right. Somebody know how those two are right? If you're thinking a little bit of a hint, think back on the way we reason things. Think specifically about deductive reasoning. Think about deductive reasoning. In deductive reasoning, we know a big statement and we make a prediction. So let's try to do that here. If you were walking along the side of a lake and you picked up a rock and you threw that into the lake, would you expect that rock to sink or float? When we did the rocks in lab, did you expect them to sink or float? You expect them to sink. Now, I know the wood floated. I get that. But in general, if you needed to make an inductive statement, and inductive statements, we call them absolutes, but they may not always be absolute. Even an absolute isn't always absolute. You can't guarantee anything, right? So we might call them 99.99% absolute. Most of the time, if you came upon a liquid and a solid, would you expect the solid to sink or to float in that liquid? Solid, liquid, expect it to sink. Now, you just used deductive reasoning, didn't you? You made a prediction. Solid things typically, usually, generally, pick your modifier, solid things sink, I almost screwed it up, sink in liquid things. Why? Density, right? It's all about density. Who's got the greater density, solid or liquid? Who remembers the definition of density enough to give me that answer? Solid or liquid, greater density in general. Solids do, right? Remember what a density measures, gram per cubic centimeter, or it could be milliliter. In other words, I don't care how big the thing is, every cubic centimeter weighs how much, right? See, that's what density is. All right, now take a look on the right. There's benzene. Look at liquid benzene. Look at solid benzene. So if you used your deductive reasoning, you'd say, okay, solids typically, usually, always sink in liquids. I therefore predict, ergo, solid water should sink in liquid water, just like solid benzene sinks in liquid water. So back to Emily and Courtney's answers, technically, right, they were correct, just like the Nazca lines being made by space aliens, right? Be very careful when you follow through on the reasoning. You can, and I'm making examples relatively ridiculous, right? But it's not always relatively ridiculous. You really got to read the reasoning out and see if it makes sense. A plus B doesn't always yield C. All right, so we know, of course, water floats, blah, blah. Why does water float? Well, it floats because it's good for us, but chemically, why does it float? All right, springy, 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 getting cooler. Springs are slowing down. Springs are slowing down. Springs are slowing down. Getting really close to one another. As a matter of fact, the springs get the least springy, the least springy at just about 4 degrees Celsius. Like 3.98, I think it is. Till what? 3.98 degrees Celsius. At that temperature, is water liquid or solid, by the way? Till what to your math class, Brandon? God, I remember when they first introduced letters. I'm like, what? You can't add letters. Maybe everybody goes through that. Come on, folks. 4 degrees Celsius. Tell me about this stuff called H2O. Liquid or solid at 4 degrees Celsius? If you're sitting there trying to convert, don't. Just know 0 degrees Celsius and the significance of that. It's a liquid. Yeah, 4 degrees Celsius. And I just told you that at that point, at 4 degrees Celsius, as Seth points out, being a liquid, at 4 degrees Celsius, water is at its greatest density. Now, the reason why I keep emphasizing the word greatest, guess what happens and when you cool it off from there? When you go from 4 to 3 to 2 to 1 to 0, and at 0 it freezes. Not at 1. My wife always says, well, the plant's going to freeze. They say it's going to get down to 33 tonight. I'm like, no, not counting the wind chill. I'm like, water doesn't say, well, tonight I'll freeze at 35. It freezes at 32, freezes at 0 all the time. So 4, 3, 2, 1, 0. As soon as those molecules are moving slower, 4, 3, 2, 1, 0. At 0, they actually pop back out a little bit. At 0, because of the way solid crystalline ice forms, reasons of chemistry, rules of chemistry, got to follow chemistry, got to follow physics. Those hydrogen bond, the distance between them ain't springs no more. They're rods. It becomes rigid, and the distance is precisely between each one 4.48 angstroms. That's what that little a with a 0. What's an angstrom? It's a really little itty bitty thing. See what I'm talking about? Therefore, that's how liquid water is going to be heavier than solid water. Because when solid water, ergo ice, becomes ice, it actually begins to decrease in density, right? Springs are getting closer, 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 density increasing, getting closer, boom, they pop back out again. Density decreases. It's really cool. Isn't that cool? What do we care about that, right? Well, gosh, let me tell you what. If we lived up north, and we were a critter swimming around in the lakes up there, we'd care. When lakes freeze up north, yeah, I love that. Isn't that neat? Some neat pictures. I love the husky walking across the frozen lake. I'll get to that in a second. You think it's a puppy? I love huskies. I had huskies. Yeah, I look at that and I go, with what I know, I think, what goes through the animal's mind, Trusting feet, trusting sight. Anyway, we know up north the lakes don't freeze solid, right? We know that. Do I have to ask that? No. So down below, is class over? Oh, no, it's not 10:50. Jeez. Anyway, down below that frozen chunk of ice, below the husky, there's liquid water, and there are fish swimming around. Now, I'm not saying it's warm, but there are fish swimming around there. So down below the ice, it's actually still liquid water. As a matter of fact, the ice, believe it or not, forms an insulator, kind of. It actually prevents the liquid water from getting any cooler than just staying at liquid water. It's why folks spray it on their plants, or orange growers spray it on their crops when the freeze is coming. The ice up next to the leaf, the temperature won't get any cooler, and sometimes the air temp might get down to 28, which is below freezing, which would wipe out the crop. And then the reason why that happens, and this goes to Dorian wondering why the shrimp. If you notice that shrimp, he's feeding up underneath the ice. If ice didn't float like it did, he would have nothing underneath to float, right? And if ice didn't float the way it did, that lake below the husky would be frozen to the bottom. Fish can't swim in solid water. Plants can't survive in solid water. When water turns into an ice, water turns into a solid, it becomes nasty, very nasty. If you don't understand what I mean, think frostbite. What happens to an appendage? Think of frostbite on a finger. What happens to an appendage when you get frostbite, like a finger? You're all going, what is frostbite? Gone. Turns purple, turns black, it dies. See, when liquid water in your cells becomes solid water, water forming those 4.48 I don't care about you memorizing the distance, 4.48 angstrom distances, that forms a crystal structure, sharp knife, cutting through the tissues in the cells, destroying the cells and the tissues. It's one of the big things that scientists work on. How can we prevent cells from freezing? How can we prevent the water from freezing? Because once the water freezes, bye-bye finger. You're destroying tissue. If you let it freeze enough, you destroy the entire cells. You all fascinated by water now? Because I got a couple more things to talk about. Isn't water cool? I mean, it's like H2O again. They're just amazing to me. I've always been fascinated by this tenuousness of nature. Whatever you call that? Where hypothermia, what, from being cold? right before you die of freezing to death, you yeah, low body temperature. Was that in Florida? Lake Tahoe, yeah. Were you in the water? Were you swimming in the water? Because that water is like ice cold. Yeah, water can remove heat from your body. It's such a good conductor of heat that that I think, if I remember the number correctly, it removes heat 300 times faster than air. So you cool off in water 300 times faster. I don't know if that number's accurate. You can check me on that, but it's a lot higher. Oh, last property before I go on. Water dissolves everything. It's soluble. All right, it has the ability to dissolve everything. So that's really important for living things, because living things do this, what was I calling it? This beautiful chemical dance in a liquid medium. Cells are full of water. So all these things we're going to talk about after we discuss what cells look like, respiration, photosynthesis, gene transcription, all that stuff that we're going to go for the rest of the semester. All of these things are occurring in this liquid medium of water. And the reason why that's so important, and water solubility is so important, is water is really good at dissolving things, right? By separating things. And that's what we want to happen, you see. Because going back to Brandon's little math problem, what we want to do is we may want to go make A plus B creates D. So now instead of those being numbers, we say substance A plus, which we ate, okay? Or maybe we made from something we ate, plus substance B now makes something we want, an enzyme that we use for something, substance C, all right? So what we do when we have this liquid medium for everything to mix, we got social lubricant, my friends, right? We got social, what's the best way to get the party to open up? To make sure you got alcohol, right? Social lubricant, everybody's moving around talking, everybody's relaxing. That's what this is going on. In solubility, water is providing that mix. Or maybe you throw a game out there. My son has bought these really cool games lately, actually kind of fun. These board games, maybe you do something like that, or you turn on the TV, or you start a conversation. Courtney, I'm sorry, except oil. Did I? Yeah, it won't. Why? Oh, good, thank you. Why will water not solubilize? That's not a word. Why will it not dissolve water? Right, exactly, Courtney. Thank you. Why will water not dissolve oil? Or the other way around? How come they don't mix? What's the word about their bonds? Ooh, there you go. Oil's nonpolar, and water, of course, is polar. And like dissolves like. So let's go look at solubility now as we drill down a little bit, see what's really going on. It's all about stickiness. Here we go with hydrogen bonds again. So they bounce around on springs to absorb and release heat. Nice. Temperature moderation. They float. Nice. Need that for those. Nice picture of that husky. There we go. All right. Terminology. A solute, solvent, solution. Solute, the thing that got dissolved. Solvent, the thing that did the dissolving. All right. So if I put salt into a glass, sodium chloride, like you see in the picture, the solute is the salt, or in this case specifically the sodium and the chloride ions, and the solvent is the water. If I put sugar into water, then sugar is the solute. If I put proteins into water, then proteins is the solute. The thing that's being dissolved is always the solute. Think about solvents. Use solvents to get rid of things. So solvents digest things or remove things, right, or loosen things up. All right, remember I mentioned to you the other day, if it says aqueous, there's a specific term for that. So when you see that in the future in your book, or I'm talking about it, remember that many things can be solvents, waters and all kinds of things. Oils can be solvents, couldn't they? What could oil be a solvent for? What kind of a solute would I need that oil would be a sufficient solvent? That's a good question. Yeah, it's going to have to be the same, isn't it? So if like dissolves like and polar dissolves polar, then non-polar things would be good for dissolving other non-polar things. Now, if it's aqueous, then it's water. I'm always talking about water. So the only thing that aqueous solutions are going to be able to dissolve are other polar things because of the water. Now, it's those hydrogen bonds again, right? See, they're sticky. And take a look. Oh, this is kind of neat. So you look at that salt crystal, right? Sodium and chloride. Sodium ions, chloride ions. Now remember, if it's an ion, make yourself little flashcards here, folks, or word lists. You know, an ion is something you need to know what it means. So if you say it's an atom, that's not enough. It's not just an atom. It's a charged atom. Sodium, when it's not charged, is not an ion. Chlorine, when it's not charged, is not an ion. They're not ions until they're charged, but because then they become a cation, the positive sodium, positive, and then negative anion. All right. Anyway, those things are sticky, right? Sticky. Not sticky like glue sticky, but all them little positive and negative ends of the water molecules and all them positive and negative and all them positive and negative ions do their thing. Look, and there's a lot more water molecules, so that they begin to surround that salt crystal, and they begin to slowly, not just one of them couldn't do it, but all the positive ends of the water molecules get around the chlorine negative and the opposite for the sodium, and they tug, and bloop, they begin to pull that stuff apart. Doesn't take very long, but guess what it does? It dissolves. That's what dissolving is. Dissolving is the thing, the solvent, ripping apart the solute. That doesn't happen in water and oil, even if they do things like put those, remember during the Gulf oil spill, they put down dispersants. And they're like, look, the oil's gone. No, not gone. Here's what happens. Dispersants actually just made the oil into smaller and smaller little droplets. You can't dissolve that oil that's in the water. It can't dissolve naturally, okay? So now all we have is little tiny, you can't see the oil as much, but it's still there. Those little droplets are kind of what I'm talking about in terms of hydration shells. The opposite of that in terms of polar things is when those water molecules go around those negatively charged ions, they form a shell. They form hydration shells, okay? That becomes important later on when we start talking about things moving through membranes. But okay, so you can water can dissolve sugars, it can dissolve salts, it can dissolve big proteins. In these pictures here, purples represent proteins, and all the little lumps there are going to represent individual protein molecules. And we'll talk a lot about proteins. But here's a big protein that you eat. Here come the water molecules. And proteins have positive parts and negative parts. They also have parts that are neither. They also have hydrophobic parts. Let's try this. And proteins can be really, really big chunks of molecules. The parts of the big protein in the picture there on the left, the big one, and of course the picture on the right is just a blow up to show you how the bonds are pulling it apart. In that protein there, would you expect the hydrophobic parts to be on the inside or the outside? I'm asking you about these guys. The hydrophobic parts of the protein, would it be on the inside or the outside? Would you deduce? Tell me why. I'm a big why kind of person, so even on exams, I'm going to want to know why. Why do you say that? From? Winner chicken dinner. That's exactly right. And that's how I'm going to hammer this into your brain when we get into proteins next week. But the most important thing about proteins is its shape. And having hydrophilic and hydrophobic parts of a protein is one of the ways that proteins maintain or get a particular shape. It looks like a blob to you and me, but that blob is a very specific blob to Mother Nature. So if you put the right parts of the proteins, if you're building that protein, you put hydrophobic parts on it, and you put hydrophilic, when you put it in an aqueous environment, water, chemistry, no biology there. Biology just put the right components together. Put the right components together, that's end of the semester, by the way. That protein automatically folds into the right shape. That's so cool, right? Okay, while we're on hydrophilic, hydrophobic, let's stick with those words for just a second, just to make sure that we have no problems. Again, hydrophobic, you don't like water, oils, waxes, fats. Hydrophilic, you do like water, things like acids and bases, ammonia, sulfur. Hydrogen sulfide is can dissolve in water. That's that nasty gas-smelling, well, egg-smelling gas. Awful stuff. Right, so as I showed down below, a really cool picture too. That's oil droplets. That's what oil does in water. So no matter how small you make those droplets, by the way, and that's what those dispersants do. They just make little tiny bubbles. You're still oil. And nothing breaks down that oil. Like dissolves like. Oh, now there's a new word. We need to talk about this word. Yeah, it does, doesn't it? All right, this is kind of cool word, amphiphile. So this is a molecule that is amphiphilic. And like I said before, sometimes it helps if, if you break down an unfamiliar word and say, are there any roots I know? I'm trying to think of a word the other day that came across me. And I was like, oh, there's a word I've never seen before. And I did that. I was going to try to remember for you guys, but I can't. But an amphibian has that root. What do we know about amphibians? Anybody know anything about them? Yes, they're frogs and toads, but they have a unique sort of way that they reproduce. Somebody know that? If not, that's cool. You haven't had bio 2. Maybe if you remember, maybe if you like. Yeah, they lay eggs. That's true. But they also have what else? Where do they lay those eggs? And where do those eggs develop? Tadpoles. And where do tadpoles live? There you go. So they have two kinds of life. Perfect. They have two lives. They hatch in water. They live as a tadpole, moving around water, feeding. Then they metamorphose. They lose their tail. Most of them. Some frogs have tails. Most frogs lose their tails, and they become land-dwelling critters. So amphib means both. And philic we talked about the other day. What was the word? Philic. Hydrophilic. That's the word I introduced. Philic, love, right? Brotherly love. So in this particular case, amphiphiles are both love. So they both love water and they're repelled by water. Ah, what the heck? How can you? Now the little picture that you see there, you're going to see a bunch throughout this semester, a ton. And that little picture is a very nice little model of a lipid, a fat that I'm going to introduce you later on, but right now is known as a phospholipid. Lipids are fats, and phospholipids are examples of amphiphilic molecules, right? Or amphiphile is what the kind of molecule we would call this. Now, why is that? Because if you notice, they have what's called a hydrophilic head. Now, it doesn't really look like this. This is just this is the Niels Bohr. Remember how he drew it like the planets? It's an easy way to explain it. And we'll come back to phospholipids. So they have a hydrophilic head, which is going to be attracted to the water, and a hydrophobic tail, which is going to be repelled by the water. So if you put those things together into a glass of water, what are they going to do? Any ideas? So it's not going to be a dissolving thing, but there is going to be an attraction thing. Anybody have an idea what that, if I had a handful of a bazillion phospholipids, dropped it into a beaker of water, what would they do? Okay, Courtney, that's good. So that's going to mean what then? So they're going to form a bubble, right? It's kind of what that oil is doing in those pictures. You see where it says like dissolves like. They're going to circle the wagons, if you will. So the tails are going to get as far away. So the heads are going to be pointing out towards the water. Is that what you're telling me? All right. So we get a situation where we get this, and then these are going to be facing away, and then right next to it. I'm not going to draw the whole thing, but this is going to go around in a circle, isn't it? Just like we see the droplets there. Now, what's missing from this picture, though? There's something else here that's a problem. Because when that bubble was formed, when these things circled their way up, guess what they trapped on the inside? They didn't trap oil because it wasn't oil they were in, but they trapped water on the inside, didn't they? So they're not going to just form one layer with their hydrophilic heads facing out, are they? They're going to form what we call, you may have seen this before, a bilayer. Right? They're actually going to look, and we're going to look at these a lot more, so I'm not going to spend a lot of time here today, but we're going to look at what phospholipids do when they form a bilayer later on and talk about why that's so important. But this is what I mean. So when those phospholipids that I threw into a beaker of water, what they're going to do is form a sphere, like you see in the picture there, that is two layers with the heads facing out and the heads facing in. Water being trapped inside and then the water on the outside. So the tails are inside of this layer of phospholipids. Phospholipids are not alive, okay? They're important for living organisms, but they are not alive. It's important I emphasize that because they have this unique ability to do something that is very good for living things, which I'll let you guys chew on when we get to cell structure. All right, we're doing well. Any questions with me so far? Everybody awake? Everybody having a good morning? So you're making your little cards, right? Hydrophilic and hydrophobic and cations and whatever that is. You're getting that all taken care of, aren't you? Excellent. Okay, little terminology. One slide. All right, I'm not going to spend a lot of time on it. You spend a lot more time on it when you do chemistry, but I do want to introduce you to these words because these words are things that you're going to see a lot more. Exactly. There's a mole. We do have moles here in Florida. Now, the mole I'm talking about here is a little different mole. It's not the critter, but it's something that actually has a value. And I've given you the word mole, and then I've showed you the abbreviation. So like kilogram is K, mole is MOL. Now, don't worry about it. It's a lot simpler than you think. Here's what a mole is. A mole is a unit. For example, like the king says, here's a rock that weighs a pound. Here's my foot. That's what a foot is, the length of my foot. So a mole has a definition. Anytime you come up and say, this is a the, you got to say, what's a the? So what's a mole? A mole is 6.02 times 10 to the 23rd molecules of anything. Big, long number. I'm not real concerned about you memorizing that number. But if I have a mole of sugar, it has that many molecules. If I have a mole of carbohydrates, it has that many molecules. If I have a mole of hydrogen, it has that many molecules. If I have a mole of moles, it has that many molecules. I guess if I have a mole of moles, I have that many moles. You understand what I mean? It's the number. This is Avogadro's number. Some dude named Avogadro who figured it out. What's that? Moral mass. Molar mass? Is that what you meant to write? There you go. Okay, now, who gave me? Yeah, Dorian. All right, check it out. Here's the easy part. Molecular mass. Now, what we do when we were calculating using moles, a mole is something we calculate based on the substance. All right, so for example, if we were looking at glucose, I'll come back to those definitions in just a second. Let's take a look at glucose. Glucose has this atomic formula. It's got 6 carbons, 12 hydrogens, 6 oxygens. Right? Everybody okay with that? So we're a glucose molecule, which we'll talk about much later, has got 6 carbons, atoms, 12 hydrogens, and 6 oxygens. It's the recipe, what we call the empirical formula. Like H2O is an empirical formula, right? Everybody good with that? All right, now, here's how we figure out what a mole is. Here's how we figure out how much of glucose, you have a mole of moles, a mole of sugars, a mole of glucose. How much glucose do we need to have 1 mole? How much glucose gives us 6.02 times 10 to the 23rd? No problem, Seth. This will be recorded. So here's how you calculate that. First of all, you go back and you write down what the atomic masses are for each one of these elements. Don't memorize that. You may have to someday. If you forget it for some reason, you have a question, I will tell you what it is. The atomic mass of carbon is 12, rounding. Hydrogen is 1, oxygen is 16. All right, now here's how you figure out what a mole is. What you do is you multiply the atomic mass times the number of atoms. So it's an aggregate score. So there are 6 carbon atoms, each weigh 12. There are 12 hydrogen atoms, each weigh 1. 6 oxygen atoms, each weigh 16. Added up, that's 180. Now you're going, what's 180? All right, now here's how you get a mole of that. Here's how much glucose you need to have 6.02 times 10 to the 23rd molecules of glucose. You go into the lab and you take that number that I just circled, 180, that you just calculated from those aggregate molecular masses. Aggregate, I'm adding them up. I'm not just adding up the molecular mass of a carbon, hydrogen, and oxygen. I'm worried or I'm concerned about how many there are. All right, so it's the molecular mass times how many. Now, 180. I go into the lab and I would draw out of the glucose bottle on a scale 180 grams of glucose. Bingo, that's a mole. I have a mole. I have 6.02 times 10 to the 23rd molecules of glucose. Easy, right? Okay, easy one for you. CO2. And you have all the information on the screen. What is the molar mass, or the mole, as Brandon said earlier? How many grams of CO2 do I need to have a mole of CO2? Do it again, Brandon. Try it again. Anybody else? All right, now show me how you did that. One of you, show me how you did that. I'm sorry, I guess it's scratching my armpit there. I'm scratching. We never do that in class. How'd you calculate 44? We're getting close to the end, folks, so stick with me, and then this will be our last thing. How'd you get? Somebody just write it out real simple. Do it like it's on the screen. Give me carbon's 12, right? CO2's got 2 of those, so that's 16. Not 16, 6. Right? 2 times 6. Oh, wait a minute. Slow down. Hold on. It's only got 1 carbon. Oh, I got you. I see what you did. All right, so carbon is 1. So carbon dioxide is 1 times 6. All right, that's the carbon, which equals 12. That's the carbon, right? So we have 1 carbon, it weighs 12, so we got 12 so far, so put that. And then how many oxygens we have? We have 2 oxygens, and each oxygen has an atomic mass, not the atomic number, as the atomic mass of 16, 32, 32 plus 12 equals 44. What do you mean, a blackboard, Brandon? Folks, we're at the end. Practice those. They're not hard. It's exactly what it is. Just look at the formula, take the rounded atomic masses, add up, you got yourself a mole. One last term, and I'll let you go. Molarity. Then we take that amount, 180 grams of glucose, for example, and we put it in a liter of water. That's a 1 molar solution, big M. Mole is little m, M-O-L. Molarity is big M. All right, that's what you do. So now you take that solute, dump it into a solvent, in a liter of it, and you got yourself 1 molar solution. All right, folks, that's it for the day. I'm more than happy to stay online. I'm going to stop the recording. So if anybody's got any questions, by all means, let me finish the recording.